I'm going to talk a little bit about the conceptual design, the seismic strengthening of buildings. And as mentioning in the morning, there are the process of this for designing structures in seismic regions requires three main stages. First, the conceptual design, then the calculation process, and the third one, the detailing, and also the last but not the least, the execution. And every stage is very important, and you cannot disregard anyone that may lead to an unsafe structure. So it is important that the structural engineer follow closely all the stages. And I'm going to try to show you this with some practical examples of my experience as a designer in structural engineer. And this is a building in Lisbon, near the river in Alcântara. And well, the architectural and the functional constraints, there were two buildings with 8 levels each, and there were many large open spaces for improving the flexibility and the versatility of the space inside. So only columns on the facade were possible to provide there. So also we had flat slabs that we know that we need space for MEP, so the installations, the pipes that are crossing in the ceiling, and also a particular situation of these two buildings. There was a steel roof covering both buildings, and what I'm going to talk about is how we solve these kind of problems. Okay. Well, the overall concept is regularity, simplicity, symmetry, and redundancy. It's very important to a well-behaved structure in a seismic region. So the large open spaces up to 13 meters led to, we were expecting higher self-weight of the slabs when compared with a common structure with smaller spans like 7 or 8 meters. So what we did was pre-stressed strips and the reinforced concrete slab between those strips, that the idea was to reduce as much as possible the self-weight of the slabs. This will reduce the weight or the gravity loads in the piles, because this was near the river and the foundations were not very good. We did indirect foundations, and also reducing the inertial forces caused by the seismic action. Also, we have flat slabs and punching failure that we know that is a problem in seismic areas. So the overall concept was to provide enough stiffness in the shear walls so that all the columns could be considered as secondary elements for the seismic loading. Okay, so the cores were located on that area. We had enough cores in the stairs, in the lift, and the lifts, so that the columns could be considered only to take a fraction of the seismic load and are not really needed for equilibrate seismic forces. The steel cover, it was a tricky situation because it was covering the two buildings and it was connected to both. So we need to provide structural systems to avoid the collapse of the steel structure because of the individual vibration of each building. So you can imagine that the cover was covering the outside area, and some earthquake could appear, the people run away from the building outside thinking that they were safe, and then the cover will collapse on top of them. So what we did was the structure was connected to a building, and we left a seismic gap, a large seismic gap of 400 millimeters in the other building, so that the individual vibrations of the two buildings will not make this steel cover to collapse. Also, we provide a Gerber beam, so it's an isostatic structure, to be less sensitive not only to the temperature, but also for any imposed deformation of the buildings due to the wind or differential settlements or else. So all this must be mainly must be made properly, and so we have the drawings. We need to pin the connection for the columns. also all the beams. This was during the assembly, they were placing this part of, it was that last part of the roof, and all these connections had these pin connections, okay? So this was regarding the conceptual design, how we think to solve these constraints that we had for this case. Obviously, we had the calculation process also. We developed a global model to check the dynamic behavior of the building. We did a response spectrum analysis. It was a very well-behaved structure. It had the first two modes with translation modes and the second one of rotational mode. And with this model, we could calculate our cores, our shear walls, the reinforcement on our shear walls and cores. And these elements are very important for seismic resistance. So you need to have much attention with them. So not only to calculate the reinforcement, but also to provide enough stirrups for confinement, especially in the corner of the walls. And in this situation, we also had a beam that were connecting here. This was the lift cores. We had others, but this was the lift. And we have some beams connecting these two shear walls, and there were coupled beams that had large shear forces and bending moments, and they must be properly detailed. So we need to provide diagonal reinforcement, and it is very important, this diagonal reinforcement, but it's very difficult to use it because we have a lot of constraints of the placing of the reinforcement, the possibility of problems of casting because you have too much reinforcement is high. So you need to provide good details so that the workers could know exactly how they are going to put the reinforcement. But if you don't put this diagonal reinforcement, you cannot guarantee the deformation capacity that you need, okay? Also, nobody thinks it's important, but the need of the stirrups to be properly bent. In the morning, also they mentioned this. It's very difficult to, at least in Portugal, to guarantee that it is properly bent. Many times I see this kind of detailing of the stirrups, and you know that this does not work well because after a few cycles of a column of an element, the spalling of the concrete cover, there is a spalling, so the concrete cover just disappeared. And if it disappeared, you don't have any way of the stirrup just open, and you don't have any way to confine the concrete core. I'm going to talk about this more time. So these are stirrups properly bent, and you think it's as easy thing to do, but it's not, because we go to the construction site, and it's not always like this they're doing. The flat slabs, how did we solve it, this flat slab? So we designed the slab to resist the punching stresses for the gravity loads combination without any shear reinforcement, okay? But then we put stirrups, and the main goal of putting the stirrups, or these punching studs, which for us is better than stirrups, we put these punching studs in the slab to improve the ductility, the deformation capacity of the connection between the column and the flat slab. That is very important to have deformation capacity in this zone, even if these are secondary elements. Another thing that we think that is not important, but to have the laps of the reinforcement lap of the columns to be in the middle height of the column, not near the connection to the slab, where we have the higher stresses and where they are the potential plastic hinges. So we need to also provide this, and you can see this here in the picture. So this is a photo of the building now. It is nowadays. Now regarding strengthening, I will talk a little bit about the building. It is a simple building. It's a reinforced concrete structure that was an industrial building, and now they want to for habitational. And it's they have some pre-stressed beams in 1961. So the project was from 1958. So pre-stress, the applications of pre-stress in buildings in Portugal at that time, there are no many applications of this. So it was very interesting to study this building. The goal was to preserve as maximum structural elements as possible, but this building was designed according to old seismic code. So the strengthening of the structure for seismic loads was unavailable. What were the potential problems? We had large spans, and you can see here within 15 meters, and no shear walls at all, so we expect large interstory drifts. We also had a lack of stirrups in the columns for adequate confinement, and the column beam connection were not, the detailing was not suitable for alternate opening and closing moments. So how to strengthening? Either we strengthening all the columns, or we provide new elements for the resistance of the seismic action. So strengthening all the columns will be a lot of work because we have to strengthening all the elements, injecting all the elements. So what we did was to provide new shear walls, so that their stiffness will be enough that the existing columns were considered as secondary elements for the seismic load, and so they were just there for the gravity loads. Okay, all the seismic action is going to be calibrated by these new shear walls. But obviously there are some columns that the section was so high and the stiffness was so high that it was not possible to consider them as the secondary elements. They carry a relevant fraction of the seismic forces. So what we did was to injecting those elements also. The strengthening of the foundations also what was needed, and we did it with the steel micropiles. And also we strengthening some beams for shear, for both for gravity and seismic loading. The importance of a proper anchorage of these steel plates. We put these steel plates around the beam, but they are properly anchored here in the top face of the column. Okay. Now this is the building like you have today, and well, and now when I was invited for this this conference, I didn't know that I was going to be in Turkey, and I'll be there with a Portuguese mission of damage survey of the earthquakes of 6th of February. And I would like to show you a little bit of my experience there, because many of the problems that I've spoken before, we could see in real time. First, I would like just to read a sentence from Nicolas Abraze. This was given from my professor Carlos Sousa Oliveira, and this sentence is very good because it's very true. And they say that the site of a damaging earthquake is a full-scale laboratory from which significant discoveries may be made by seismologists, geologists, engineers, sociologists, or economists, not to mention politicians. Well, for me, as a structural engineer, it is really a full-scale test. You can see the structures, the damage, you can understand the failures. Huh? And that's what I want to share to you now. This was the team. It was a group of people from academia and from professional. Also, he had some Turkish people there. Well, we went in 2 months later, we went in April of 2023, and we visit all the affected area. The main affected area was here. And well, what happened there was in the beginning, there was a major earthquake at 4:17 in the morning, the worst hour to have an earthquake because everybody is at home sleeping. And there was a major earthquake with the epicenter here, and a few minutes later, 2 more earthquakes occurred, was 6.6 and 7.5. Nevertheless, 9 hours later, another major earthquake of 7.6 magnitude in the north part of the first one. And it's curious because there are not many events in earthquakes that they repeat a few hours later. Another earthquake with the same magnitude. And then 250 kilometers south, 2 weeks later, another 6 earthquake of 6.5. Obvious that between these, there were thousands of aftershocks, but with slower magnitude. And you can see the comparison here between the design response spectrum for return period of 475 years. This is this black line. This gray line is for 2575, so more or less 2500 years, the return period. And the blue line and the red line are the measured spectral accelerations. In the blue line is the east-west direction, and the red line is the north-south direction. So you can see this was measured in several stations. This one was over here, and you can see that in many cases the measured accelerations were higher than the design. You can see here this case, and well, this case is incredible. I don't know if there is a mistake, but this is a good source. But you can see that it's very large. The design accelerations were very lower compared to the measured ones, and also here. I'm going to talk a little bit about, it seems like that there is a shift on the response spectrum with the maximum acceleration. And, oh, well, what we saw was buildings like this. This was not the worst case, but this was in Skanderoo, and it was recent construction. Skanderoo is a very healthy healthy city. These houses are very expensive for Turkish people. So there was residential buildings with 12 to 16 floors and with cores and shear walls. So the natural periods of these buildings was between 1 to 2 seconds. And when we tried to compare what happened with the measured design spectrum with the measured accelerations with the design accelerations, we can see that there is a little bit shifting for the maximum acceleration more to the right. So we have between 1 to 2 seconds. That was the natural period of these buildings. It can double or even triple the design acceleration. So many buildings are still standing. You can see here that you have bending and shear failure here. Okay. This is one of the many soft stories that we saw. So this was a commercial area, and well, the building was like this when we arrived there. And there are many situations like this. I have some videos that you can find in the YouTube also of many. This was the second earthquake, so in the afternoon. And well, you can see here that we had a soft story and then the entire collapse of the building. And we have a lot of situations like this. Many soft stories collapses were reported. And you have many cases like this. Okay? You can see this in YouTube also, these videos. Anyway, if you can look at this, this is a problem. This is a case where probably the conceptual design should think a little bit more, because this building had it's a 7-story building with a large core in the back facade of the building, okay? And the front facade of the building has columns, a frame system, so columns and beam. And what we saw was that it was a torsional flexible system. So the building has torsional effects. And what happened, we had plastic hinges in the beams that were formed here, and also plastic hinges in the columns. And because of this torsional effect, what happened is we had in the columns, in the corner columns, that's the one that suffered more because of the torsional effects, we had a failure in this column in the smaller width, which is very important because sometimes we don't think in the capacity design in this direction. Anyway, another situation, this building was in the final stage of the construction, a new building, according to all the codes, okay? And what happened is the designer said, okay, I have an L-shaped building, which is not good, it's not symmetric, and I'm going to put a seismic gap here to have a rectangular one and the square one. For now, it's okay, but the problem was that the seismic gap was not enough. And it didn't avoid that the building pounding. So what happened is that the larger building was okay with minor damages, and the smaller building was completely damaged. The infill walls just collapsed, major plastic hinges in the beams and in the columns. Anyway, it is better to do the seismic cap, do not to do it, okay? This is an example. This is a picture before and after. So what happened here, we don't have sufficient seismic gap. And what happened is that this slab in the middle height of this column just pound against this column that caused the collapse of this building. So it's better to have a seismic, a seismic gap, okay? And sometimes we look at it and it's a kind of a lottery, it's random. Some buildings collapse, others no. These were 4 identical buildings that were under construction, and they looked like this before the earthquake. They were putting the infill walls, and one of them just collapsed. You see a flexor, a bending and shear failure here, a clear shear here, but this one collapsed. The structure is equal. Obviously, more knowledge is necessary, because why does this one fall, collapsed and the remaining now not collapse? Anyway, the buildings, oops, sorry. The remaining buildings that had permanent deformations. So they probably, I was thinking that, okay, thank you. That permanent deformation, and probably they are going to be demolished, okay? Under the situation that were in a city there were dozens of residential buildings like this, with all of them with similar construction type, like frame system, no shear walls. And what happened? The building was okay. Well, many non-structural elements just flew out of the building. They collapsed, out of plane collapsed, but they had shear walls in the beams, but no shear walls. The shear potential, they had plastic hinges in the beams, but not in the columns. But since they have large interstory drifts, what happened is that things that are connecting the different floors are the stairs. So you can take a look at what happened to the stairs. So people are running away because the building was shaking, and the stairs, don't go by the lift. Go by the stairs. I don't know. The stairs were not designed for this. So we need to think about this. So shear walls are important. The conceptual design with shear walls is important, okay? Detailing problems. We saw a lot of detailing problems, like lack of, oops, sorry. The insufficient anchorage length, and you can see the pigeon ears, so you can understand the scale. That's the reason this slab just collapsed. You can also see that the lapped bars were always done in the high stress zones in the columns. So many failures like this, you can see the reinforcement here is starting and it's finishing here. So this stress is in the plastic hinges. So we need to avoid that. That's the reason we put the lap reinforcement of the column at the middle height. And things like this, if you don't properly bend, this is what happened. The stirrup just opened, the concrete core just explode and disappear. In this case, where the stirrup was properly bent, the concrete core was still there. There were another case, the lack of legs. Pedro Cabral also talked about this. We need more legs. You cannot have many longitudinal reinforcement without any stirrups. Otherwise, they will buckling. And something that we don't even think about, the non-structural, well, many people do not think. I know that the new Euro Code is going to have something about this, but all the non-structural elements, and this is crazy, because I saw too many damage and collapses of non-structural elements. The exterior brick wall. So imagine people running away from the building. They were outside. They think, okay, I'm safe now. No, they are not safe, because one of these brick walls may fall, may collapse. In other cases, interior infill walls, they were in very bad shape. This case is very interesting, because before we have this, and after, all these finishes collapsed, and collapsed in the front of the office of the building where the people was going out. They want to exit, but the the exit was blocked. All the false ceiling content, solar panels, other equipments, all of them are in very bad shape. This is a good example of an hospital, and all this finish, exterior finish, just on this state. The hospital was not operational, mainly to damage to non-structural elements and to the malfunction of the medical equipment. Okay, so here we had a collapse of the emergency stair, which is anyway. I will leave you with some thoughts. Huh? The first thing is nowadays we have in the code that no collapse of the structures. Okay, so for the engineer, a structure that does not collapse is a good solution. But the question is, does this meet the public expectations? Okay, the people that live in the house think, okay, when a seismic occur, I will never have a home again, because the structure is not the structure or the building cannot be strengthening. It's basically demolished and to build again. So is this what general public think? Maybe we should start to shorten the gap between what is the structural safety for an engineer and what is a seismic resistant building for the public. Okay. Now another thing is how I'm a designer. How do we design a structure for 2 earthquakes with a similar magnitude? I don't know how to do this. So maybe some knowledge. And the only non-structural elements that we design, at least in Portugal, are the lifts and the facades when there are important facades. So maybe we should think a little bit about this also. And who checks if the structural project meets all the recommendation? Maybe a peer review process should be included in our design. And also, who checks in the construction site if the rules, if the details are doing according to the rules of good practice? Because many engineers in the construction does not know that we need to bend the reinforcement. Okay, and also after these results, I think that Turkey must think a little bit of revising the spectral accelerations. Okay, now just 2 small videos. One video, it was the first earthquake, and this was in Camamaras, and you can see a few seconds, and a building over there is going to collapse. I don't know, 5-10 seconds of the earthquake, and the first building just collapses. And you can see this is a camera, and you can see the things obviously shaking. But what I would like to show you is to see this part that you see many people getting away from this building. They are frightened, but you can look that they have many difficulty on running because the soil explorations are very big. So to run away from this, they had to grab something. They're almost falling, and now I think that we should look at this. I know that someone already talked about base isolation, but it was Dortia Hospital with base isolation. It was the same earthquake. And I think that to avoid such a social disaster, maybe in the future, we will have all the buildings with non-conventional seismic protection, at least in high seismicity zones, okay? But you can see that the building starts shaking a little bit. And but obviously the base isolation or the other non-conventional seismic protection, we should start first with most important buildings that the hospitals fitted, because they need to be fully operational after a major earthquake. So you can see the difference between the people that were running before and the people walking in this hospital with base isolation. So you see a woman with this child, and you see this bed that has wheels, but even though it's moving just a little bit, and the earthquake is more or less similar, okay? And you can see people running, obviously that some people are a little bit more afraid and more in panic, but you don't see the kind of, I have to grab something, otherwise I'm going to fall down. So you can really understand the accelerations that the people felt was much lower, and now everybody is getting out of the hospital. This was Dortia Hospital that I have the possibility to visit it and to check all the base isolation, okay? So, gracias, muchas gracias, and thank you.